I'll start out with my acknowledgements. I'd like to start by thanking my academic supervisory team. Dr. Richard Kennaway and Professor Andy Day have been very helpful with the academic side, developing the papers and developing the dissertation, which is currently something I'm in the middle of right now. So that's kind of scary, but hey. And we're at the University of East Anglia and Norwich in the UK. I'd like to thank the Jython team, because given the fact that a lot of my program is Java for graphics and performance reasons, developing Larch without Jython would have been rather difficult. I'd also like to thank the authors of the Apache Jericho HTML library and SVG Salamander, which I use for HTML import and SVG rendering respectively. The purpose of Larch is to ask the question, what is the future of programming tools? Some of you may have seen the talk Invent on Principle by Brett Victor, where he demonstrates how by altering code you can see the effects of these alterations live. And he was able to demonstrate give some very convincing demonstrations of how this can improve program productivity. Some of you may also be aware of Light Table by Chris Granger and his recent success on Kickstarter. Once again, he's asking the question of how can we reformulate our IDEs towards programming in specific domains. Field is another interesting Python-based development environment, although it's not so well known. It's by Open-Ended Group, a group that used to be based on MIT, and it's primarily used for art projects. The Larch environment is still a research project, and to be honest, we're still in the proof of concept stage. Everything I'm about to show can be downloaded as open source. It's all available on Bitbucket and from the project website. However, I'm afraid to say it's not really usable for any real work yet. But I hope you're interested in what I've got to show, and that this potentially whets your appetite as to what we might want to have our programming tools look like in the future. And we're going to explore forms of programming that go beyond just plain text. Currently we're used to just text editors, and a lot of them even still use fixed-width fonts. Let's see what we can do if we make, well, a lot of us do, but a lot of us, let's see what we can do if we can make programs look more like an interactive book. So, a quick summary of what we're going to see this morning. We're going to take a look at the programming environment first very briefly, just to set the scene and just to give you an idea of how the system works. Then we're going to look at how we can produce visual output as opposed to the text-based output that we're used to in a console and we're used to getting from print statements. Then we're going to ask how can we present objects in a visual fashion. Then we're going to move on to visual programming, and that's where things get slightly interesting. And finally, we'll just have a quick demo of Python programs as interactive documents. So, a quick look at the programming environment. The core of the Larch programming environment is a worksheet. And a worksheet mixes rich text, code, and execution results. The rich text should be fairly familiar to most of you. You'll have headings, normal text, titles. You can also highlight certain areas and make them bold and italic. It's quite simple, sort of word processor style editor. But in the middle of this rich text, you can just embed a block of Python code, which is executed in place, and the visual results are displayed inline just below the code. And you get quite a neat workflow as well, because if you want to find out what the effect of modifying a piece of code is, just make the changes, hit F5 to refresh, and the execution results will quickly all completely change in response to your modifications. And I'm going to give you a demo of what the worksheet looks like right now. Okay, I'm going to switch to developer mode because that makes all the code editable, otherwise it's just for show and you can't change it. So, very simple text-based output, uncomment it, F5 to refresh, we get the output. Once again, F5 to refresh, we get the changes, and they're all in line. Simple mathematics, very similar. Nothing that exciting yet. So, let's see what happens if we want to look at some images. Here we have some code that uses the Java image IO library to load some images from the disk. They're found using the glob module, and they're then placed in a Python list using this list comprehension here. So, just for comparison reasons, let's take a look at what the images look like if we pass them through the toString, which is normally provided by Java. This overall is not terribly informative in a way because, well, you've got a lot of information about the color model, the bit depth, the width and height of the images, but it's just a big ball of text. If we show the actual list itself, though, we end up with the images inside a Python list, They're separated by commas and surrounded by brackets, and we can even then zoom in to see them at full res. I use the Java AWT Vector Graphics API to render everything so I can just zoom and scale in as much as I like. Whoops, okay. So I think that shows you that having visual output in certain circumstances is somewhat better than the equivalent text. Let's have a look at something slightly more interesting. What about a cellular automata, which is a very simple simulation? We have some imports here, and here we define our cellular automata class. Its constructor just takes in the various parameters like a color map, the number of cells in width and height, cell size and pixels, initialization and evolution functions, and it sets everything up. Our evolve method steps the simulation. Our draw method, given a Java graphics object, will draw the cellular automata to the screen. Now, this one's important, so you want to remember this one for later. This is the double under present method. And we'll get into this in a little bit more detail later on. To give you an idea of what it does, it creates an animated drawing of the specified width and height. It provides a function for drawing the contents, a function for stepping the simulation, which just invokes the evolve method, and the amount of time elapsed between each time step, and then places a border around the whole lot. We then give some sample initialization and evolution functions based on random numbers. And if we uncomment this, refresh, we end up with a nice little animated cellular automata just below our code in the middle of our document. And we can even then change it and make the colors really horrible. F5 to refresh, and it looks ghastly. And I heard Harry suggesting fuchsia. Isn't that lovely? And just for later on, I'm going to make it slightly smaller because we'll need a smaller one later on. We'll leave it with that nice, disgusting color scheme, just because it's so nice and we like it so much. Okay, those of you who have experimented with either Mathematica or EuroPython will notice a very strong similarity between Larch worksheets and the notebook systems of Mathematica and EuroPython. Similar workflow, similar idea, and they work very well for certain domains. And they're also a good experimental system, since you can just write code and you get the visual output straight back, and the fact that you can quickly edit, refresh, makes a kind of convenient system for just developing your ideas. Alright, now let's move on to visual output, namely, how is it built? Visual output is built with presentation combinators and style sheets. The word combinators might be unfamiliar to some people, although if you come from a functional programming background, you'll probably know what they are straight off. A combinator is effectively, it's really simple actually. It looks like a function when you use it, when you call it, and it simply combines various different constituent parts to make something slightly more elaborate. And I'll show this later on. And the style sheets, well, they're a bit like CSS, so probably a lot of us know what they are. And presentation combinators describe a visual presentation that's to be built. In similar way, HTML tags describe DOM elements that are to be built within a browser. It's the same idea, only within Larch, the presentation combinators come in the form of a Python API, whereas in HTML, the tags take the form of the angle bracket notation. And this is roughly how they work. This is just a quick demo. You construct the label with the text hello. You just get the text hello back. You give an image the path to an image file, and you just show it displays an image. If we then construct some labels, we've then got containers. These are the composite combinators. So row, we'll arrange them horizontally. Column, we'll arrange them vertically. There are more than that available. We've got paragraph layouts that do the automatic reflowing of text or anything else in there as well. It's not fussy about what you put inside a flow layout or any other kind of layout, whether it's an image, text, or something that you've built out of other combinators. You've also got tables, grids, flow grids, mathematical fractions, superscripts, and you can even build your own. You can build composite ones out of the simpler ones and keep building more complex stuff. There's a whole bunch of rich text ones are built. The controls are built out of these as well. So all the various little buttons and checkboxes can be built of these components. It's quite a simple system. And effectively, it's like building visuals using a Lego brick style construction technique. And I'm going to demonstrate that now with how we're going to build a diagram that describes the process of the Gaussian blur. Is anyone here familiar with systems like Photoshop or the GIMP? Because if you've used that, you probably know what Gaussian blur is. It's a basic function that just blurs an image. Okay, well, we'll go to developer mode again. We create a blur kernel here. We'll get down to what that is later. But we'll uncomment this to get the result. And this little diagram here is what we're looking to build. And to show you what the Gaussian blur does, I'm now going to explain roughly what it's all about. We've got this source image here. We convolve it with this kernel here. And the result is a blurred image. As for how that works, when you want to compute a pixel in the result image, you take the equivalent pixel in the source image, and you then compute a weighted average of its surrounding neighbors. And this kernel here, this table, these are effectively the weights of the various neighbors represented from black to white. Black meaning no weight, 0. White meaning full weight, 1. Then you've got this weighted average of all of the neighboring, of the pixel and all its neighbors, and that's how you get the blur. So, how are we going to build this nice little diagram using presentation combinators? And that's what we're going to look at now. Okay, well, where would be a good place to start? I think perhaps a good place to start would be to look at how we build one of these little blur cells here. And to do that, we have a function called blur cell that takes the weight, constructs a grayscale color from it, uses that to make a filled border, which is simply a border that fills in the background, and places that around an empty space of 8 by 8 pixels. And the result is a blur cell of half gray is a small cell of half gray. Now here we have a nested list comprehension, which takes our kernel, which is just a 2D list of floating point values between 0 and 1, which is our list of weights, our 2D array of weights, and we use a nested list comprehension to construct the blur cells for those weights. And we end up with a 2D Python list of blur cells. Now we use the table combinator to arrange those spatially in a table, and we end up with that. And we can see how our little diagram of our kernel is made. Here we see the figure combinator. It takes the first parameter, in this case an image of the source image, and then places a caption beneath it. The result is this, image with a border and the caption. Same thing for C, our result image with the caption. But also, we've got table blur created our visualization of our blur kernel, and that results in the diagram, which is figure of B. So this is how we construct our 3 figures. This space here is simply just creates some blank space for you, and if we then arrange A with the space with the operation convolve, well, I should probably show you what that does. The operation simply takes the text, places it above an arrow. Oh, and that's centered just because of the fact there's an align center call up there. And if we arrange all of these in a row, we end up with this. And I hope you can see how that's quite a simple API for constructing visuals, just sticking things together from smaller parts until you end up with a nice representation. And that allows you to build things up from small parts to hopefully get something approximating what you want. In contrast to other systems, I'd say in contrast to, say, GTK and Swing, the code you get is somewhat more terse. In GTK and Swing, when you construct all the various buttons and checkboxes, you quite often have to create them, then you have to set the style attributes. Our style sheets do that similar to CSS, where you just set a style sheet for the presentation, and that provides all the various attributes controlling the appearance and behavior of the elements. In addition, quite often when you construct the composite elements that arrange things in rows inside GTK, you then have to add all the children afterwards, whereas with this you just pass them to a constructor. So you end up with a very, very terse, simple code. It's pretty much like HTML and XAML, and some of you may have also heard of Enthoughts Enamel, which is similar to things like HTML, similar to systems like HTML and XAML, except however it uses a Pythonic syntax. It's really quite cool, and I suggest you check it out. Our system, though, we have a slightly different design philosophy in that you get the full power of Python programming language. You can use functions and classes and loops and list comprehensions and whatever else you want to use in order to build your presentations, which you can't quite do if you're using HTML. You have to end up sort of using a mix of of template languages and joining strings together. So this can be slightly more convenient in some ways. But CSS, for instance, deliberately didn't employ the full power of a programming language, therefore removing the possibility that you get into infinite loops, infinite recursion, and just bring the system down. So take your pick as to what you like. Now, what about presenting, say, data that's contained within objects? What I've shown so far isn't quite sufficient. Functions and classes aren't quite enough yet, so what can we do about this to move further? So let's move on to presenting objects visually. If you want to display data from objects, what would you guys say is the most commonly used design pattern for achieving this? But about visually, representing an object visually, like in a GUI? Like common architectural pattern?
An outline of class?
MVC, model view controller, exactly. Thank you. And there we go, it's the basic MVC diagram that's been in use since the 70s, or 80s, whenever it was come up with by the Smalltalk guys. But it can be quite heavyweight. You've got to separately implement your model class, which contains your data. You've then got to implement your view, which constructs all the elements that present the data visually. You've then got to, sometimes you'll implement the controller separately, which takes the user input and feeds back to alter the model. And it can be quite a lot of work. And have any of you found in your experience in the past that you would really like to produce something visual, but then you kind of don't bother because it's too much work to actually write all the MVC? And have any of you found that? Yeah, I certainly have. And one of the problems is you've got to explicitly create the right kind of view for the right kind of model. If you've got a person model that represents a person, you want to create a person view for that. And then within the person view, if you want to review the address, you've got to create the address view within the person view. But if you then want an editable person view, you've got to create an editable address view. You've got to explicitly create the right kind of view all the time. And it can be kind of a, well, it's not so much of a pain, it's just extra work to do and extra things to get wrong and extra bits of code that are slightly inflexible. So, well, our approach is we use something commonly used in Python. We use type coercion. And type coercion is just the process of converting an object from one type to another, from whatever type it is to some destination type. And it's using things like reparent str, which converts a Python object to strings. It's using index, which converts it to an integer for indexing into an array. And within Larch, we coerce objects into something visual. In our case, a pres, which is our base class for presentation combinators. Now, as for how do we use it, how do we incorporate an object in our presentation? It's really, really simple. You just literally put it in the middle of the presentation description like that. If person is just a regular Python object and A and B are presentation combinator types, like say labels, just simple presentation types, Larch will automatically coerce person to become a visual representation of that person. Now, what about if you want to actually customize how an object is presented? How do you how do you tell the system, in this particular case, my object that I've just implemented, I want you to show it like this? You define the present method. Remember I told you to remember the present method from the cellular automata? Well, that was what was going on there. That was how the cellular automata was saying to Larch, this is how you display me. And that's how that works. So think about it as similar to str, like a visual version of str. And trying to get visuals to the point where they're similar in complexity to implementing a str or a repr method is what I was trying to achieve. And for Java objects, you implement the presentable interface that defines a very similar present method that does the same thing. We can also handle objects in the standard libraries as well, but with no monkey patching. So with monkey patching, what you might have to do is you might have to take the class and then say, after the fact, I'm going to add a double under present method. That can be kind of nasty, and for Java as well, you can't even quite do that because all the classes are baked and sealed once they've been declared and created. So what we have is like a little registry of presenters, and it takes the object, it uses its class as a key to go and look up the right presenter. So and in fact, that was how those images were being displayed earlier. When I load the images from the disk and put them in a Python list, they were just ordinary Java buffered image objects that don't know how to present themselves with Larch. But by registering the appropriate presenter, you can just make them display themselves quite nicely. Perspectives. In case any of you were concerned that how the heck do you present things in different ways, like different views for the same model in MVC, this is the Larch equivalent of that. The approach we've taken is slightly different. because different perspectives in Larch represent different intentions. So just as I was giving the person model versus person view and editable person view, you'll have two different perspectives, the view perspective and the editable perspective. And what they will do is they will then present objects that are given to them either in an ordinary way or an editable way, or whatever their intention is. So we kind of factor that out into a different place. The perspective that I've shown so far, the one that uses double under present or the presentable interface, is what I call the default perspective. And whenever you give something to Larch to say, show this, it uses the default perspective by standard. So if you just declare a double under present, that's just the easiest way of making any object visual. But when you declare your own perspectives, you can use your own methods or anything you like. We also do automatic incremental consistency maintenance. Bit of a mouthful there. Put simply, auto-refresh. So you may also be used to the fact that when you develop maybe a web app or a GUI app, that often in response to state changes in the underlying object, you have to then go in and say, well, I've got to modify my visual representation to take that into account. If someone sets a Boolean field, I've got to go and say, oh, that Boolean field's been changed, I've got to go and modify the state of the checkbox that's displaying it. What we do is we do something slightly different. We tell Larch that the object state has changed, and Larch maintains a mapping such that it knows which object is mapped to which visual representation on screen, and it goes and schedules the refreshes of the relevant parts of the presentation for you automatically, so you don't have to bother. It's just less work to do. When you invoke the presentation by type coercion process, for example, when I had that example, when I had the row A person B, when that person object was coerced into a visual representation, and automatically a model view relationship like an MVC was established, and it will automatically refresh the presentation of that person when Larch is notified of a state change. And everything you've seen in Larch so far is just objects being presented via this technique. The main home page with all list of projects, the projects themselves, the worksheets, the source code, so it's a fairly flexible technique. I found it to be quite useful. It's also fairly scalable as well because the code it's represented as a collection of lots of little objects, so you can have thousands of them active at once. It's no problem. Let's do a simple demo of how to use this. I'm going to develop a very, very simple photo album, or show one that's been built. Okay. Alright, we'll skip the imports, and we'll start with an annotated image, and I'll show you what it looks like down here. We just loaded the arrow SVG, and it's got this little description at the bottom. Now the constructor up here takes the path to the image, loads it in this line and places it in the IMG attribute, and also creates a description by taking the file name. And notice that incremental monitor. This is how you tell Larch about state changes. And now we've got our ever-present method. We notify the incremental monitor of an access. That's important. This is how you tell Larch that you want to monitor the state of this object in order to refresh this particular piece of presentation. This is how it's able to establish the relationship between the two. And it's able to get that automatically. It does that via some global lists. This is where we create the annotation seen here. We take the description, we build an editable label. That simply is if the description has never been set before. And this function is notified when the user changes or edits it. We then apply some styles, place a border around it, and then we overlay the annotation on top of the image, and we end up with the result here. And we can even edit it and just change the name. When we hit return, what happened was this onDescription change function was invoked, the description attribute was modified with the text provided, then the incremental monitor was notified of the change, and the annotated image was automatically redrawn and refreshed in response to that. Notice no mutations. It automatically redraws the entire thing in response to any changes. So I didn't have to specifically say what to redraw. I just say change, therefore please redraw this object, and it'll re-invoke it with a new in order to refresh the presentation of the object according to the new state. I hope you don't mind if I move on to the next part, which is the image list, or the image collection rather. Now we've got this drop images here box, which is built here, and it's appended to a list of images which is currently empty. Once again, we've got our incremental monitor, but what we effectively do is we place these in a flow grid, and we attach two drag and drop destinations. So I'll show you what that does. If I take these images here and select them, drag them over, and they just go straight in. To show you how that worked, I tell the system that I want it to receive a list of files from drag and drop. It's going to call that function when it happens. It takes the data, which is a list of files, list of Java file objects, gets the file names, creates an annotated image for each one in this list comprehension, and then bolts it onto the end of the images list and notifies of the change, and it automatically updates. And that's as easy as it is to create a drag and droppable little simple photo album. But we can do other things as well. There's another drag and drop destination in there, which is provided here, and this describes a drop destination for just about any object within Larch. And in fact, if I go back to my cellular automata, what I'm going to do is I'm going to Alt-Shift drag this over, and we can even drop that in as well. Now notice that we've got that cellular automatas working in there. By holding Alt-Shift, I told Larch, I want you to get the object that's presented in this part of the visual representation and just allow me to drag it somewhere else. And what this drop does is, we'll notice that it just appends it onto the end of images. And this is where the tight coercion MVC kind of really comes into play. I didn't have to specifically say, oh, you're going to need to be able to display cellular automatas here, or display images. I just to say, display whatever's in this list, just arrange it in a flow grid, and Larch will just automatically take whatever it's got, figure out how to display it for you, and just put it there. You don't have to explicitly say what to display and how to display it, like you do with the typical sort of MVC approach. Now, let's make things slightly more exciting. Visual programming. It's got quite a rich history in the research community. People have tried various techniques. There have been, say, for example, circuit diagrams, such as in the system LabVIEW, and that's been quite successful with its users. There have been attempts to develop data flow diagrams and various other approaches as well. Now, they've been quite successful in their own domains. Non-expert users have liked them quite a lot. And they've been often been quite nice for small, simple programs. And for programmers like us, they work well for a simple program like, say, I don't know, Fibonacci. But the moment you've got a large program, like, say, 100,000 lines of code, you end up with a diagram that's the size of that whole wall there. You've got links everywhere, so it looks like a rat's nest, and you've got this tiny little monitor screen to pan and zoom over it. And that's why I'm afraid to say these things have never really scaled up. It's known as a scaling up problem, and not many people have come up with a good solution to it. And as a result, text remains to be the dominant medium for source code. But what about technical literature? Think about the last time you looked at a science book or a computer science textbook. It's mostly prose, it's mostly just text. But however, you've got diagrams, tables, and spatial layout where they're helpful. So, why can't we do the same thing for code? Why can't we just have text-based code most of the time, but where it's helpful, we're going to use visuals and diagrams. So let's see what we can do. I'm going to demonstrate this. I'm going to demonstrate what we're dealing with first. We're dealing with simple polygons, 2D polygons. I apologize for scanning through this code rather quickly, but this interactor here simply takes an input from the user, namely button clicks. It draws a polygon to the screen, and it also responds to mouse events. And the result is we use it to drive this polygon, which is presented by its present method here. I'm going to rush through, I do apologize, but the result is we end up with this nice little interactive drawable polygon that we can add vertices to. So, well, how can we use this? If we go back to our example, which is our definition of a function called convex, that removes all the concavities from a polygon. Imagine, say, you're doing a room plan. A concave room plan is a room in which you can stand anywhere in the room and see everywhere else. There aren't any kind of any walls butting in that would block your view. So the idea is you've just got a convex shape as opposed to one with concave areas knocked out of it. And these two this helper function and this function take a polygon and return the resulting polygon, which is its convex hull. So here's an example test of the function. We call the convex function of this polygon, which is constructed here, of this list of points. Quite a few of them quite a few of the points have been removed in order to make it convex. But how are you going to visualize what this polygon looks like? Well, you better get a piece of graph paper and draw it out, because it's the only real way of doing it. And that's kind of a pain, especially when working in the graphics area. So how can we improve things? Well, why don't we just put the polygon straight inside the convex call? And then we can just see the result here. And we can even then just go and edit it. Notice this polygon is within the brackets of the convex call. We hit F5 to refresh, and we see the result. We can even put our own polygon in by deleting this. Okay. Whoops, developer mode. We'll make this slightly more interesting, and then what we can do is, using our Alt-Shift-Drag trick that I showed you earlier for the image list, we can just pick this up, drop it in the middle of the code, and there it is. So this shows how we can develop a visual object and then just drop it in the middle of the code and just have it there. And we now have visual objects and diagrams inside our source code, which is getting towards what we want. How did that work? How do we do this? We just embed the polygon or any other object within the code. And to the compiler or to the surrounding code, it just looks like a reference to an object. So that convex function call just received a reference to the polygon that was embedded within the code. And the visual presentation system, as shown earlier, will just display it in line. Just like the type coercion within the inline objects within the image list automatically coerced either the images or the cellular automata into something visual, the same trick coerces the polygon into a visual representation as well. So you can just create any object, define your present method, and then just drag and drop it in. Easy. Now, what about something more useful? Does anyone else here hate the regular expression syntax? Does it confuse the hell out of anyone else here? Oh, good. Why don't we see if we can improve things a little bit? The syntax is going to be the same, but we're going to see if we can use visuals to make things a bit better. One second. Let me drag that window out of the way. Okay. A typical regular expression. Isn't it lovely? And and one of the things about regex is you might look at that bracket. Now, obviously that doesn't actually match a bracket. That's part of a character set. But whether it's the end of a character set or a bracket depends on how many backslashes it's preceded by, which is kind of a pain. One thing in Larch, though, if you do happen to enter backslashes, it does highlight all of the escape sequences for you, which does make them slightly more usable. But still, having to figure out whether that bracket's going to actually be a bracket or an escape bracket or whatever is too much of a pain. So what happens how can we improve things? Well, I'm going to put in a visual regular expression, and I'm going to paste that in, and we'll see that it's now been rendered with various boxes and borders that highlight the structures of the regex. So you'll notice that the yellow borders will highlight the choice operators. You see the bars there. The blue boxes represent character sets, and the green boxes represent groups. The slightly grey-green boxes are non-binding groups. These ones bind the group to a name, and the little pink boxes, they represent repetition. And in fact, you can even just type into it. So I can just, and I'm just entering code quite normally, and it just parses it as I go and inserts it into the structure. And in fact, even if you don't have an actual use for Larch itself, just because my environment's a little bit strange, you can even paste it into a text editor just fine, and you can paste back and forth, and you could use that as to assist you in developing your regular expressions. So you can use that so you can see the obvious structure of them a bit more easily, and then you can just copy and paste between your text editor and just use that as a tool just for that, even if you have no other use for it. And so. And for my next trick, I'm going to make Perl readable. Just kidding. So embedded objects can also use a protocol to customize their behavior. If you embed it as a literal, what you've got to imagine is that, say, when I've created the module, at start time I snuck in and took my embedded box object that you see there, the little purple box, and I've bound a reference to it, to the name box at the top, to a global variable called box. So when you see the function call of f of the box inside on Larch, the Python interpreter gets f of box. As an expression, you can define a method called pyeval and customize the way it's evaluated. So when you have that regular expression, you actually get back a string because it defines a pyeval method that effectively says, I'm going to return a string, so to your code you just get a string back, despite the fact it's something more complex. You can also customize it such that it behaves like a statement, like say assert or print or give me some others. Anyone? Could be anything. So you can define pyexec, which allows it to execute like a statement. We can also create objects that represent pieces of editable Python code. So you can just say, I want a piece of Python code, and when you display it, you get this nice little editable box, and you can edit code in it. And so if we can create an object that represents code, and we can put objects inside code, we can stick code within objects, within code, within objects, within code, within objects, kind of like a Russian doll. And what that means is we can freely mix code with visual objects. A bit Lispy in a way, but visual. So anyone who's familiar with the Lisp macros, we're getting there. And who else finds unit testing can be a bit tedious? It may be awesome, but it can be annoying. So I'm going to give you the sort of motivation for this particular demo. I'm afraid to say it involves a bit of parsing. Who here is not familiar with parsing? Anyone not familiar with parsers? Cool. Well, the purpose of a parser, just to quickly give a quick explanation, is to convert some text like that into a structure like this. Now, I hope you don't mind the way I've decided to display my trees. In order to make them look like the mathematical expressions, I've taken the various different expressions and I've put them in boxes, but trying to keep the sequence the same, but you can see how the various binding works. So the multiplication operator binds more tightly, so it puts its box around the b and the 2 first, and the add adds the a and the b times 2. So does everyone understand the structure of the tree, the concentric structure? Is this not clear to everyone? Anyone? Okay. That's good. And in order to, the way my parsing library works is if you describe the patterns that you want it to match, like say match this particular character or this particular word, and then match the sequence of these, and then what you can also then do is you can provide actions that build the necessary objects that represent that. So this is how you might say start with this and convert to that. You match the various patterns and then you use the actions to build the objects. So now let's look at what we have if we use ordinary text-based code. We've got our helper functions here, which you'll see soon, but we won't go into them. But the way my system works is I have a grammar class, and I declare the rules as methods, and this is where I declare my various patterns. And this is the example of an action where I provide a function that will build the necessary node, the tree node that represents my structure. But we're here to talk about unit testing, so I hope you don't mind if I skip down. Now this is the typical kind of unit test. We select the right rule, we tell it to parse as input, we get the result, and we verify that it's equivalent to that. So far so good, except what happens when you start to get down here to the really nasty stuff? We've got this fairly complex compound expression, and oh dear. Anyone here want to volunteer to type that out by hand? Anyone? No, I had to, and it wasn't pleasant, believe me. No, it's not fun, it really isn't. So how can we make things a bit better? Well, that's a good answer. Well, this is my solution. You'll notice also that my unit tests were either below the class or sometimes you put them in a separate file. In this case, my unit tests just sit right alongside the code they test. I've got my code to create my parser, I've got my code that creates my input, and then I've got the expected result and whether the test either passed or failed. Notice that this success or fail that's not talking about the state of the unit test, that's talking about whether it successfully parsed the input or whether it failed to parse the input. So sometimes you give a parser invalid input and you say, I expect you to fail to parse that. So fail there is actually good. So let's scroll down and find the scary ones. They're down here somewhere. Where are you? Here you are. So for a start, we've got this nice visual structure representing our expected output, which I think is a bit easier to read than that huge nested pile of text. And well, what about how do we type it out? The answer is we don't. You see, this table here acts a bit like a spreadsheet. So if I want to create a new unit test, I copy that, paste it down there, make my changes, but how do I set my expected result? I actually don't bother to do that. You see, I decided I want to be lazy here. I hit F5 to refresh, and it tells me I haven't got an expected result, but I got this. And it's inviting me to please visually verify that this is the correct result. And I say, yeah, that looks about right. I say, set expected result, it transfers it over. And from now on, all my unit tests will test it against that. So if I go and screw up my code later, it'll pick that up. And if I just do that and I change that to a 5, if I just, that's fine, that's passed. Now if I change that to a 5, hit F5 to refresh, it now says fail. And if I want to update my expected result, I just go over here, click the spreadsheet cell, delete it, F5 to refresh, and transfer it over again. And that's it. And so that's how you make unit tests, with a kind of visual interactive unit tests embedded inside your code. We can start to see how we end up with sort of visual interactive documents. If we're ever interested in debugging our parse, we can click this trace link and get a nice visual explanation of the parse trace, and that tells us how our parse proceeded by rendering a nice little graph in GraphViz. So we can further sort of provide extra debugging tools. Okay, I better run ahead because I'm running out of time a bit. And so you've seen the spreadsheet-based unit testing. The embedded objects kind of they're kind of embedded by both runtime and compile time, so it's an edit time object was able to receive results of unit testing and update its visual representation, which is like edit and compile time. So they kind of cross the barrier between the editor and the runtime. You might have heard of how Ruby is used for developing domain-specific languages, and JetBrains, MPS, and Intentional Software's domain workbench are similar, and that's for DSLs. What Larch does is domain-specific Python, and you kind of saw that with the unit testing. That was kind of like a little customized version of Python, just for unit testing, but with a GUI. Now we move on to Python programs as interactive literature. What if we say we wanted to make some API documentation? Well, you're probably used to seeing it all as HTML, where it's just like a static document or a book. But I think we can do something slightly different. I'm going to demonstrate my presentation API as an interactive document. Now this is just a regular document. We've got some code here describing how you use it. I'm going to spin on a bit. Sorry about that. But we can now see some demonstrative examples of how our API works. You saw the presentation combinator that I described earlier. Here, we can just go into this table. We hit Control-Enter, and it updates. So you can see here how we have example of code, the result you expect to get, but you can even go and edit it and find out and experiment with it and try out new approaches. We've got demonstrations of the style sheets down here, so I can just go and change that font size. See the result immediately. So I've now got this interactive, explorable API documentation where not only can I understand the fact that is definitely how it works. It's never going to be out of date because what the result you see in the right column is always going to be the result of evaluating the code on the left because that's what it's doing. But also you can then change it as well and experiment with it in line. And so I can even just go and maybe just copy, paste. And there you go. And so I can even add new examples as well and just experiment with the API inside the API documentation. And this can go on further. I would have liked to have demonstrated how I can cut and paste my initial Gaussian blur and place it within a cell. You can do that, and you just get the full diagram, but I'm afraid I've run out of time. Can I quickly rush through my conclusions? Is that all right? To conclude, we've got a simple compositional approach to UI description, namely presentation combinators. It's like Lego bricks for visuals. Auto refresh means you can automatically keep stuff up to date. You've got tight coercion that massively simplifies object presentation, or at least it does for me. The nice thing I found about developing Larch is I never have to worry about MVC anymore. I just say, put this here in relation to this, and then I just say, this has changed, and it updates it. It takes care of all that stuff automatically. I don't have to worry about it anymore. It's nice. partially visual programming. Maybe this is the kind of visual programming that could work. Let's do it like a book does it. We've got interactive graphics, visualization, MVC. They can be scary to implement normally, but I think things can be better. Interactive visuals really should be a natural part of the conversation that we have with our computer when we program. We're used to just using text. Why can't we just have interactive GUIs being part of that conversation as well? So let's take the console into the 21st century. And I think if they're easier to create, we'll create more of them, we'll use it more often, and we'll get more out of our computers as a result. And I think if we can then just drop the middle of our code, our program is going to be easier to understand because we can use visuals where they benefit our understanding, and it's going to make our programs a pleasure to write and use. And there's a lot to do. There's documentation, bug fixes. There's no story of how you use version control, and it's basically a research prototype. So the idea is, let's test the ideas, let's put them out there and see what people think. And I've got a bunch of demos if time allows, so if there's enough time after questions. Thank you very much.
Questions for the program? Okay. Can you justify the heresy that is using a proportional font to program with?
Justify the heresy that it is a proportional font? I'm not sure why it was a heresy in the first place.
It's wrong, isn't it? Obviously, what? That's not what we do. It's just not what we do. If you can use a microphone, because
using proportional fonts is wrong. I disagree, just because with proportional fonts you can fit more text in the same space, you can read it quicker. Now, interesting enough, I did do a quick private demo to the BDFL of this on Monday, and he commented that probably a fixed width font would benefit the regular expressions because the hyphens would be more obvious. I agree there are certain domains where they benefit, but I don't necessarily think that proportional fonts are wrong for code. I think they're not. Why do we use proportional fonts? Is it tradition? Is it because that's what we've always done? Is it just because of the fact that we're still sticking with these 1970s interfaces? I don't know.
Thank you for a nice presentation to begin with. What I would like to know is, this is a running application on your computer, and we're moving towards more like web programming, and you mentioned EuroPython in the beginning, and that's also displaying things on the HTML canvas, so to speak. Could your program do that in future? Or do you have any plans to do that?
It's a very good question. A few different answers for that, really. Getting things to run reliably cross-browser is scary because of the various different problems of DOM manipulation. I didn't show this to you, but the thing is, though, my code is actually not stored as text. It's actually stored as an abstract syntax tree, and there's an editor on top of it that just presents it as text and makes it behave like text. Getting that to work actually took 2 or 3 years. It was my initial part of my project. You need to have a lot of control over the way your presentation system works, and you don't get that with HTML. You'll have to fight against the system a lot. Now, most people might say, yeah, that's not necessary. And in some ways, they'll probably be right. Writing a Python editor like that is too much work. But you also lose that funky visual regular expression editor because you kind of need it for that. But however, that said, if anyone's interested, I haven't open sourced it yet, but you know the kind of type coercion and automatic refresh and all that kind of good stuff. With significantly reduced presentation combinators, i.e. just bits of HTML, I've got a web-based version of that working. And so that's not open source yet, but it's written and it works. And so within a browser, you can just have an object update and it'll refresh the presentation. So that does work already.
Maybe turning that into a browser.
Yeah. So, yeah, it could be done, but, you know, for code, I think we'll just use Code Mirror. But how we do visual updates embedded in code, don't think I've got a story for that on a web browser. Not yet. It will require a lot of work. A lot of JavaScript, not fun. Sure.
Yeah, but the proportional font thing, I guess it's usually, you know, just get back into it. There's a cultural thing coming from terminals and Usenet and text emails and stuff, but obviously there's also a very direct technical requirements because, you know, Python uses indentation, and it's kind of hard if you have different width of different characters and different lines to really align things correctly. So that might be a reason. Maybe it's less important such a visual environment, but still might be a problem, I guess. yes. But anyway, I quite like whatever you did here, so that may be a secondary thing, I don't know.
As far as indentation, let me see if I can find a quick example. Maybe it's here. Maybe this will do. Yes, here we go. Notice that it does automatic structural indentation anyway. So it just reflows and it does structural-based indentation. So you'll notice that it's aligned to all the imports there. So rather than have tabs, I mean, effectively, when you want to edit something, you have to, you know, the indentation there is specified as 30 pixels or something rather than a few spaces. So I think this is a different approach. So proportional fonts, I think you can use them. And my indentation width is more of like a rendering option rather than a number of spaces. I think maybe that's the way to go, or it would be nice if we had that, you know, in all our editors, such that, you know, you could have your own style. You know, rather than, you know, you and I disagreeing on the number of spaces we could use, it could just be a style sheet option. It renders it the right width for you and the right width for me, and, you know, we both get to use the same code and see it presented the way we like. So maybe a structural model for code is good. I don't know.
It's back to tabs.
Not exactly. In a way, it's structural, so it's indented in this. It's encoded in the structure rather than using tabs or spaces. But yeah. Any other questions?
Yeah. First of all, thank you for the great stuff. It's really impressive. I just have that idea. When I saw you out commenting and in commenting, I just was wondering why you wouldn't mark something and use that as the thing you see. And that leads me also to the question how to debug that. And I thought of there should be some means where you could step through and highlight something and display it. That would be an even more tremendous interface, I think. Because you just commented out one thing in and out, and that is, I think, kind of tedious. And just highlighting, I think it's a simple change that you can make and will be even more impressive. And this regular expression, you should put it on the internet, on a website, I guess. And that other idea, no, it was not an idea, it was just a comment that with unit tests, you wrote that, and after you have a code working, you can create unit tests for it. But it breaks the unit test first approach, right? Of course, that's not possible. You have to have working code, and then you generate your tests. But it's also good. It's better than having no tests at all. But there's a, well, some of the benefit of test-driven development goes away. But for maintenance, it's just tremendous, right? So thank you so much. It's a great stuff.
Oh, pleasure. Thank you.
So there is one question there.
Okay, well, thank you very much as well. And maybe you can elaborate a little bit more on what kind of projects you would be targeting for that actually use your system. And that would lead me to the question, well, I found the stuff with the API very impressive. And is it also possible for me to just, well, port my code into your environment and then maybe use it for a lecture or stuff like that?
It depends. If your code will run on Jython, that's just what I'm using, I'm afraid. If it'll run on Jython, I don't see why not. You could use this to create interactive presentations. I would say this could be quite good for that because you've seen what I've been able to do with it. It would have to be something that's well suited to this kind of style of system. So, you know, I have to admit I've cherry-picked examples that highlight the benefits. So the presentation API is an obvious candidate for making interactive documents. I think you possibly could do that. I don't see why not. But it does bring in the problems with how do you integrate this with existing projects. Because there's no story for source control, because of the fact that although you can export a project as text files, as ordinary Python text files, you know, I haven't really got a good workflow for how you maybe interact and keep working with a bunch of teammates who are still using Emacs, say, for instance. So if you're willing to sort of create your little interactive presentations and lecture slides just within this sort of Larch ecosystem, which is very limited and very small, then I think it could be possible. But I'm not going to go out on a limb and say definitely yes to you. It's still a research prototype.
You can copy and paste a whole bunch of Python code in there. It's all right.
Copy and paste can work, but not so well. But if you can import, yeah, you can import a file. And that'll go in, and you can copy and paste from that import file to somewhere else. Because of the fact, I'm afraid, because I develop my stuff as a structural editor, you actually find all the indentation gets lost when you actually copy and paste from a text editor. But if you import the Python file and then you copy and paste it from a different place in Larch to another place in Larch, works fine. So I hope that answers that.
Yeah. So we are running out of time, and at the moment I say if you have more questions you can ask the presenter later in the room change. And thanks for the great stuff and the brilliant presentation.
Thank you.
Thanks. Bye.